In December 2010, a team of scientists at NASA's Jet Propulsion Laboratory sat down with new data from Voyager 1 and found something that, by every physical model they had access to, simply should not have been possible. The outward speed of the solar wind, the constant stream of charged particles blown outward by our sun, had slowed. Not slightly, not gradually tapering off the way models predicted it eventually would, near the edge of the solar system. It had dropped to zero. The particles were no longer moving outward at all, sitting instead in a strange, stagnant equilibrium, as if the boundary of our entire solar system had simply stalled in place around the spacecraft. Stimatios Krimigis, a physicist at the Johns Hopkins Applied Physics Laboratory who had spent decades studying exactly this kind of data, put the situation in words that don't often make it into official NASA statements. "It's certainly not what we thought," he said. "This is the real story of the strange region Voyager 1 entered on its way out of the solar system, a place so far outside what existing physics had prepared scientists for that some of the researchers studying it admitted, on the record, that nobody actually had a model describing what they were seeing. And what came after that admission turned out to be even stranger than the moment that prompted it. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why this specific region caught scientists so completely off guard, you have to understand what Voyager 1 was actually doing out there, and how long the road to this exact moment had already been. The spacecraft launched on September 5th, 1977, on a mission built to last around 5 years, a tour past Jupiter and Saturn before falling silent. Instead, it kept flying, and in December 2004 it crossed something called the termination shock, roughly 94 astronomical units from the Sun, the point where the solar wind's outward speed abruptly drops as it begins colliding with the resistance of interstellar space pressing in from beyond. Crossing the termination shock put Voyager 1 into a region called the heliosheath, the outer, turbulent layer of our solar system's magnetic bubble, and based on the model scientists had built up to that point, this was expected to be a relatively well-understood, if turbulent, transitional zone, a kind of buffer between the solar wind's dominance and true interstellar space beyond it. It didn't behave that way. Starting around 2010, 6 years after crossing the termination shock, Voyager 1's instruments began recording something existing models simply hadn't anticipated. The outward velocity of the solar wind, which should have continued at some reduced but still measurable pace through the heliosheath, instead kept dropping year after year until it reached, by the team's own measurements, essentially zero. Rob Decker, a co-investigator on Voyager's low-energy charged particle instrument at Johns Hopkins, explained what the team had been doing to track this decline, describing how they had been using the flow of energetic charged particles measured at the spacecraft's position as a kind of windsock, an indirect way of estimating the solar wind's actual velocity, even when their more direct instruments couldn't measure it cleanly. And what that windsock kept telling them, update after update, was that the wind, for all practical purposes, had simply stopped blowing outward at all. Krimigis and his colleagues turned to every available tool to try to make sense of what this meant, including cross-referencing Voyager's own readings with data gathered by an entirely different spacecraft. They combined Voyager's measurements with observations from the ion and neutral camera aboard NASA's Cassini spacecraft, then orbiting Saturn, an instrument capable of detecting neutral atoms streaming into our solar system from beyond its boundary. Using that combined dataset, the team made a preliminary estimate that the actual boundary layer separating our solar system from true interstellar space likely sat somewhere between 10 and 14 billion miles from the Sun. But the estimate itself wasn't the unsettling part. The unsettling part was Krimigis' own assessment of what the zero-velocity reading actually meant physically. This boundary, he said, had caught everybody by surprise, because not even a working theory existed that predicted interstellar gases would mix with solar wind particles moving at almost zero velocity in this specific way. He went further, raising a possibility that genuinely unsettled his own colleagues. It was possible, he suggested, that this strange, stagnant region actually was interstellar space, and that Voyager 1 might have already crossed the true boundary without anyone realizing it, simply because nobody had a model capable of describing what the spacecraft was actually measuring. Read that carefully, because it's worth sitting with. A senior physicist, working with real data from humanity's most distant operating spacecraft, was openly telling colleagues and the public that existing science could not confirm or deny whether a historic milestone, the literal edge of our solar system, had already been crossed because the data didn't match any model anyone had built. That is about as direct an admission as you'll ever get from a professional scientist that reality had, for the moment, genuinely outrun theory. The following year, in 2011, NASA's Voyager team went public with a term for this strange, unpredicted stagnant zone, one that captured the genuine uncertainty surrounding it. They described it, in their own official language, as a kind of cosmic purgatory, an in-between region where the outward push of the solar wind had calmed to almost nothing, where the solar system's own magnetic field appeared to be piling up and compressing rather than smoothly fading away, and where higher energy particles native to the interior of our solar system appeared to be leaking outward into interstellar space even before the spacecraft had definitively crossed any recognized boundary. Voyager had, by that point, been tracking a specific and genuinely strange trend since mid-2010. The intensity of energetic particles originating from inside our own solar system had been steadily declining, dropping to roughly half of what it had measured consistently over the preceding 5 years, as though those particles were quietly draining away into the space beyond. At the very same time, the spacecraft recorded something moving in the opposite direction, a 100-fold increase in high-energy electrons arriving from elsewhere in the galaxy, diffusing inward from outside the solar system, a second independent signal pointing toward the same. Unsettling conclusion. Whatever boundary Voyager 1 was approaching, it wasn't behaving like a clean, simple wall. It was porous, leaking material in both directions simultaneously, in ways nobody had built into their models beforehand. By 2012, the picture sharpened further, and the region earned a second, more specific nickname from the mission's own science team, a magnetic highway. Edward Stone, the mission's project scientist at Caltech since 1972, described exactly what made this newly identified zone so distinct from everything Voyager had measured before it. Inside this region, he explained, the sun's own magnetic field lines had become directly connected to the magnetic field lines of interstellar space itself, creating an open, unobstructed channel. That connection allowed lower energy charged particles originating from inside our solar system's protective bubble to freely zoom outward along these connected field lines, while higher energy particles from beyond the solar system simultaneously streamed inward along that same channel. Stone offered a vivid comparison to describe what conditions had been like just before Voyager reached this specific zone. Charged particles previously trapped inside the heliosphere had been bouncing around in essentially every direction, as though confined to local roads with no clear route out. Once inside the magnetic highway, those same particles suddenly had a straight, open path, zipping directly in and out along connected magnetic field lines, the way traffic might suddenly find an open freeway after being stuck on winding side streets. And Stone was candid in the same public briefing about how far this specific region had diverged from anyone's actual predictions. The new region, he said plainly, isn't what we expected. He added something that, in hindsight, reads almost like a mission motto. But we've come to expect the unexpected from Voyager. That's a genuinely remarkable thing for a mission's own lead scientist to say publicly, on the record, at a major scientific conference, about a spacecraft his team had already been operating for 35 years at that point. It's an open admission that the models built from decades of careful, peer-reviewed theoretical work, models built by some of the best heliophysicists in the world, working entirely from indirect observation because no instrument had ever actually been out there to check, simply hadn't correctly predicted the specific physical structure this region actually turned out to have. The magnetic highway also came with its own internal diagnostic clue about how close Voyager 1 actually was to finally crossing into true interstellar space. The Voyager team specifically noted that despite everything strange happening inside this new region, one critical measurement hadn't changed yet: the actual direction of the surrounding magnetic field lines. Existing theory did predict, with reasonable confidence, that the direction of the magnetic field should shift measurably once Voyager finally crossed the true heliopause boundary and entered genuine interstellar space. As long as that directional shift hadn't shown up in the data, the team inferred that Voyager 1 was still technically inside the sun's broader environment, however strange that environment had become, rather than having already crossed over. Stone's own best estimate, based on everything the team understood at the time, put the actual crossing somewhere between a few months and a couple of years further down Voyager's path. It turned out to be closer to the shorter end of that estimate. On August 25th, 2012, Voyager 1 finally did cross the heliopause, the true boundary marking the edge of our solar system, though NASA didn't formally confirm that crossing until September 12, 2013, more than a year later, after painstaking analysis of the spacecraft's data. That delay itself tells you something about how difficult this specific transition was to interpret. Voyager 1's own plasma instrument, the tool that would have most directly and immediately confirmed the crossing, had actually been damaged years earlier, back in 1980, during the spacecraft's flyby of Saturn. Without it working, researchers had to rely on indirect evidence instead, and the confirmation ultimately came from an unplanned, almost lucky event. A coronal mass ejection that erupted from the sun in March 2012 finally reached Voyager 1's position 13 months later in April 2013, and that solar disturbance set the surrounding plasma ringing with detectable oscillations. Don Gurnett, the University of Iowa physicist who ran Voyager's plasma wave instrument, and his team were able to use those oscillations to calculate the electron density of the plasma surrounding the spacecraft directly. Gurnett later described the moment his team actually saw this specific data come in with genuine visceral excitement. He said the team literally jumped out of their seats when they saw these oscillations, because the reading showed the spacecraft was sitting in an entirely new region, comparable to what theoretical models had predicted for true interstellar space, and totally different from anything measured inside the solar bubble. The density reading came back more than 40 times denser than the plasma found inside the heliosphere, a number that matched interstellar space and nothing closer to home. Working backward through the data using that confirmed density reading, the team pinpointed the actual crossing date to August 25, 2012, more than a year before NASA felt confident enough to formally announce it. Even after that confirmation, the region of Voyager 1 had just passed through kept generating fresh surprises that no existing model had fully anticipated. Detailed analysis of the boundary itself found that its particle signatures didn't simply flip cleanly from solar system to interstellar in one smooth transition. Instead, Voyager 1 appeared to cross back and forth over the actual boundary line multiple times across roughly 30 days, as the heliopause itself flexed and shifted position relative to the spacecraft, a genuinely dynamic, moving structure rather than the fixed, static wall most people picture when they hear the phrase edge of the solar system. And once Voyager 1 was confirmed to be firmly inside true interstellar space, its instruments recorded conditions that broke yet another set of prior assumptions. Near the heliopause itself, charged particles became trapped and compressed into pockets of extraordinary heat, sitting immediately adjacent to other regions that remained comparatively cool, creating an uneven, patchwork structure of a hot and cold plasma unlike anything ever measured inside the heliosphere. Researchers gave this specific thermal structure its own vivid nickname too, describing it as a wall of fire, capturing the genuinely unexpected fiery clash of energy found right at the boundary of everything our solar system contains. Layered on top of that came another magnetic surprise. The magnetic field lines Voyager 1 detected just beyond the heliopause appeared stronger and more tightly organized than any existing model had predicted, suggesting the interstellar magnetic field might be pressing inward against our solar system's protective bubble with considerably more force than researchers had previously assumed, actively shaping and warping the heliosphere's overall boundary the way pressure might warp the surface of a balloon from outside. Even years later, this general region of space kept producing anomalies scientists hadn't fully anticipated. In 2020, Voyager 1's magnetometer registered a sudden, unexplained jump in the intensity of the magnetic field embedded in the surrounding interstellar plasma, while its plasma detector simultaneously measured a corresponding rise in plasma density. Adam Sabo, an astrophysicist at NASA's Goddard Space Flight Center and the magnetometer's principal investigator, offered a physical explanation for this specific pattern, describing the underlying mechanism using a simple, direct image. The source, he said, behaves like a piston, with surges of plasma streaming outward from the sun, slamming against the heliospheres. Boundary, generating pressure waves that ripple onward through interstellar space, compressing the plasma out there and intensifying its magnetic field as those waves pass through. So here is where this genuinely leaves things, honestly, grounded entirely in published research and the direct, on-the-record statements of the scientists who lived through each of these moments of genuine surprise. Voyager, très en course. One spent years between roughly 2010 and 2012, passing through a region of space that multiple senior physicists, publicly and repeatedly, admitted did not match any existing theoretical model. Cremigas said plainly that nobody had a model describing what they were seeing. Stone said just as plainly that the region wasn't what anyone had expected. And once the spacecraft finally did cross into confirmed interstellar space, it kept measuring things. Extreme, patchy heat, unexpectedly strong and organized magnetic fields, sudden density spikes years later that continued testing and revising the physical models scientists had built from decades of purely indirect Earth-based observation. That is not manufactured drama. That is the honest, repeatedly documented experience of a research team watching real data outpace real theory again and again as a 50-year-old spacecraft kept pushing further into a part of the universe no instrument had ever actually measured directly before. If this kind of story is what you come here for, one grounded in exactly what NASA's own scientists measured and admitted in real time, rather than exaggeration, hit subscribe and turn on notifications, because there's clearly more of the real universe left that our models simply haven't caught up to yet. Drop a comment telling me which of these unexpected findings surprises you the most, and share this with someone who still thinks the edge of our solar system was already fully understood before Voyager 1 actually got there.